Good afternoon. Today we're going to be discussing the understanding of radiocarbon dating through the natural exponential function. Archaeologists over the years have used the natural exponential function to date fossils on digs. One good example of this comes from Glen Drive, Montana, at the Hell Creek Formation dig. At this dig, they dug up a Triceratops and wanted to age the Triceratops. Well, it was a Triceratops horn, right? So, from Montana. So the Triceratops obviously loved Montana. So this Triceratops horn was old. It was really super old. We're talking like over 30,000 years old. And they date this stuff by using a radioactive carbon. Scientists have a number of ways where they try to figure out how old stuff is and determine the age. And this one uses C14 carbon, or radioactive carbon. Now this carbon, the C14, is made in the atmosphere when it reacts with radioactive particles. So it's floating around up there in the atmosphere, it's carbon-12. It gets hit by radioactive particles, it's carbon-14. That in turn is absorbed by plants during photosynthesis. So this photosynthesis occurs, and now the plants have it. The plants are eaten by animals, and now the animals are starting to absorb this carbon-14 at a rate that stays constant. Now after the animal dies, the carbon-14 is unstable and begins to deteriorate. So that becomes like kind of a decay. So who developed this? Who discovered this? Dr. Willard Libby, in his undergraduate, read a paper that really interested him about it. And in 1949, Dr. Libby began to publish and come up with the idea of the rate of decay and half-life on carbon-14. So from 1949 to 1960, he's working on this. In 1960, he figures it out. 1960 figures it out, wins the Nobel Prize for chemistry, and everything's going great. You know, he's setting the standards. He's got all his scientist buddies high-fiving each other. There it is right there. Bam, Nobel Prize. Here goes his scientist buddies setting the standard. Everything's going good. This is what people use. This is how they date, now. So it's the gold standard, really. The gold standard of dating, the gold standard of everything along those lines. So a good example of this is he publishes his book. It's carbon-14. It's the rate of decay. It's half-life. So the half-life of carbon-14 is about 5,730 years. Okay, so we can apply this to an equation to figure out and determine exactly how to do that. But before we do that, let's take a look at this graph. At 0, obviously you have 100% at 0 years. At 5,730 years, 50% is left. So then again, at 11,406 years, only 25% left. Now divide that again at 17,090 years, 12.5% is left. So now at 22,920 years, only 6.25% is left in the system. So N naught is the number of atomic particles of of carbon-14 in the original sample. So NT is going to represent the number of carbon-14 atoms left after time T. Okay, obviously. So we can put this into equation. NT equals here it is right here, the law of decay equation, as I call it. So we take the 1 half-life of carbon-14, and it's about 5,730 years. And so N is 5,000 times 5,730 is half of the natural log. So we apply the law of decay to that, and we come up with the rate of decay. So the rate of decay is what we're looking for our R. So the rate of decay equals the natural log of 2 divided by 5,730. There it is right there. So the equation here, including the rate of decay, governs the decay of carbon-14. So here's a graph, a more accurate graph that any number can be applied to. So any number along the timeline can be applied to that. That's it. That's how you do it. That's how it's done. So let's see some examples. So our Triceratops, again, let's go back to that. So we have our Triceratops here, looking good. We have our horn. How old is the horn exactly? We want to know exact dates. So 1.81% of the original C14 or carbon-14 is left in this Triceratops horn. So now let's just apply it. Let's just apply that to the equation. So we're going to go ahead and throw it in there. So that's our equation with our rate of decay. So if there's 1.8% of C14 remaining, then N equals 1.8% of N naught. So here we'll change it to a decimal, 0.018. Okay, we're going to cancel the N naughts there. We're going to take the natural log of both sides. So we multiply by 5730, and then we divide it. That left us with 33,164. 33,164 years old. That's how old our dinosaur bone is. That's how old our Triceratops horn is. So we did it, guys. Good job. So what do we gain from this? That's the question. Now we have a better understanding of archaeology and dating and how they achieve that. We also learned some chemistry. We've discovered the application of carbon dating. We've learned more about the exponential function. Not only that, but natural logs. We also use real-world examples to date, forensically date something. So those are all really great things, and I hope you enjoyed, and thank you for watching.